So first, I'd like to thank the organizers for having me. My name is Paul Stanish, and I work in the Radovanovic research group. We do a whole lot of everything when it comes to semiconductors. Specifically, my work, though, is on finding or developing a single chromophore white light for LEDs. To understand my project, though, we need to understand lighting. The bottom right-hand panel is an incandescent light bulb. You've probably all grown up with it. But recently, the government of Canada has started to phase it out because it's very, very inefficient. We've started to move more to the compact fluorescents, which are the screw light bulbs on the top left-hand side. They have much more efficiency, but they sacrifice color quality, meaning they don't accurately represent what the light of the sun is, what we grew up with. More recently, though, LED light bulbs have emerged, being able to break out of this traditional trade-off between efficiency and quality, with the Philips bulb shown in the top right. There does still exist a bit of a trade-off, though, and that's largely for manufacturing reasons. To understand this, you need to understand how white light is made. In your art classes, you probably heard that if you take red, green, and blue, you'll get white light. That's true, but it's a little simplistic. In truth, you can make white light with only 2 points if you look at the diagram on the right-hand side. By picking any 2 points and connecting them by a line and just varying the intensity of light from either one of those points, you'll make any color along the line adjoining them. So if you take, let's say, 480 and 580, that will give you white light. Problem is, though, if you look in the top left panel, that a white light from only 2 sources or 2 chromophores doesn't fully fill out the spectrum. And this leads again to a much lower quality of light. To give you the higher quality, you end up having to go to maybe 3 tiny monochromatic LEDs together, or even more. This adds inefficiencies in electron scattering at interfaces, normal resistance, and it makes them a lot more expensive. This is how our TVs show color. But if we made our LEDs like we made TVs, we just get LEDs that cost as much as TVs. So what's done now is using a single LED as a base and putting materials or phosphors that absorb and re-emit at a different color over top. This, again, gives us the same difficulty because there are some losses intrinsic with absorption. However, this is what people who are making LEDs nowadays tend to use. But typically, they use materials, gallium nitride as the blue LED, which ends up being reasonably expensive to produce, as well as some materials in the phosphors, rare earth metals that can be a little expensive, as well as not having a very large supply. This can lead to both higher costs now, as well as much higher in the future. Obviously from this, though, we know that the less materials, the less chromophores you put into a light, the more efficient it should be. And that brings us to how we're planning on making the single chromophore white light. By coupling 2 materials together using a process called FÖRSTER resonance energy transfer, we're able to excite a donor directly and then have it emit at 1 wavelength, as well as an acceptor then receive the energy from the donor and emit at its own proper wavelength. In so doing, we're able to create from either a single electron or from a single photon white light. For FRET to work, though, you need to have the ability for these 2 materials to interact with each other. This means you need some spectral overlap, meaning the emission of the donor has to be at approximately the same energy as the absorption of the acceptor. And this spectral overlap determines the amount of FRET that you'll get. So once you have that, you can calculate the FRET fall-off when you have materials at a certain distance from one another. Now that we know how to couple them, we just need to know the materials. How can we combine the high efficiency and quality into a single chromophore? I think everyone here knows the answer, and it's nanotechnology. Our first material of choice was gamma phase gallium oxide, and we chose this because it has a very broad emission, meaning that by itself, a lot of the spectrum will already be filled, leading us to have a very high color quality. It also has the ability to be tuned with size, meaning that we can make sure we get exactly the color of white that we want and need. It emits by electrons and holes being trapped at surface defects, and the electron attraction between them, pulling them back together at a certain energy given how far apart they are. You can see here that we have reasonably good control, making a very monodispersed sample, as well as, within about the 3 to 6 nanometer range. The first generation that we used with these gallium oxide nanoparticles gave us white light that looked like this. We started off using organic dyes because they were reasonably simple to attach to the surface. And we found very good evidence of fret, as can be shown from the spectral overlap. This gave us very high color quality. However, rhodamin B, the dye that we chose, isn't particularly thermally stable. And these initial prototypes, they got reasonably hot. One of my colleagues, just out of curiosity, dripped some water on there and it boiled instantly. And rhodamin B decomposes at 80 degrees Celsius. Clearly, that's not going to work. So the next material that we chose, still starting with gallium oxide, is cadmium selenide, cadmium sulfide core shell nanoparticles. One of the reasons is because they have very controllable red light that emits very strongly, and they're used already in record-setting LEDs that were produced by this lab in MIT. And also, they have extremely strong spectral overlap with gallium oxide as well, meaning that this fret process should be easily preserved. To make the initial phosphors, we took gallium oxide made in solution, as well as cadmium selenide made in solution, and combined them. At that point, they were dropped onto a surface, either quartz or glass. And as you can see there, when you change the ratio of one to another, you dramatically change what color you get. When you have a ratio of 1 cadmium selenide to 1 gallium oxide, it looks very red. And when you have a ratio of 1 cadmium selenide to 16 gallium oxide, you end up getting blue. This is even more obvious when you look at the emission spectrum, where you see the left panel is in solution, and the right panel is on a substrate, where they're forced to be confined and right near to each other. In so doing, you see a very strong shift of the emission towards the cadmium selenide. So what we're working on now is making similar prototypes to the rhodamin B LEDs using the cadmium selenide, cadmium sulfide, and analyzing their efficiencies for efficiency and color quality, at which point we'll need to optimize the device architecture, but also we're looking at applying an electric field to these materials and using the stark shift that generates, being able to tune the color of the LEDs in the device, essentially making a smart LED. Anyways, thank you for listening.